Hello. Oh, and welcome back to Stat 3050, University of Wyoming, online. And let me tell you what, we're having a good time. Okay. So last week, or I guess the previous topic, we were looking at t-tests and all the different versions of t-tests and kind of getting an idea of what we're doing in statistics, right? We've got a sample and we want to figure out as much as we can about that sample and see if we can apply that to the whole population from which our sample came, okay? And with t-test, we were working with two groups. We were just making a comparison between two things, okay? Um, differences in heights between males and females, differences in muscle density between males and females. We could have done that with some of the data we were looking at. And what else were we looking at? What was the example? Oh my gosh, I'm totally blanking. Oh yeah, reaction times in pilots, right? We had some paired data there. We had all sorts of stuff, right? However, oftentimes, at least in sort of modern day statistics, you're not just doing comparisons between two groups. Sometimes you're comparing more than two groups, or often you're comparing more than two groups. You might have three, you might have four. You might be comparing like a ton of groups. For instance, if you wanted to see the difference in incomes across all 50 states in the United States, then you're making a ton of comparisons there, not just two, right? And how do we handle that? Well, we have this very cool tool called ANOVA, and it's short for analysis of variance, okay? And we'll start off with the simplest version, a one-way ANOVA. However, since when I say simple, I don't necessarily mean not used all the time. This test right here is used very frequently, and we'll get into more sort of advanced versions of this in the future. But for now, we'll stick with sort of the most robust sort of, okay, and easiest to wrap our heads around. It's pretty sweet. Of course, though, before we really get into it, we've got a new topic. That means new music. Oh my gosh, it's my favorite part. So we'll come down here to the old Spotify, check it out. Okay, so this is a little different, and I'll try not to talk about it for too long. But this is a little different than the music I normally recommend. This is Imagina, and it's by Rita Paez and Elizabeth Roma. Now, mother and daughter, they're a little family band. And let me tell you, these two people are probably the most talented musicians that I've listened to in a really, really long time. This whole thing is great. So they're both from Spain. So naturally, they do a lot of songs in Spanish. But also, if we come down here, they are so talented, so jazzy, and so low volume too, and such a good way. We've got all sorts of songs from all over the world. So original songs by them, but also if we come down here, we've got some Carinhoso is a Brazilian tune in Portuguese, Senhorinha also Portuguese, but also we've got some classic English jazz tunes as well, which is awesome. I think this album is really great. So check it out. If you're looking just for a nice kind of, I don't know, you could study to this, you could have dinner to this. Oh my gosh. If you're just looking for something new, a little different, I think this is it for you. So before I go on and on and on, let's just get into some stats, I guess. Okay. So here is visually sort of what we are doing. Okay. So typically with the t-test, we were doing just two comparisons. We were kind of seeing how much information overlapped between the two groups that we were looking at. Well, now what we're going to be doing is we're going to be looking at more than two groups. Okay, so three or more. Okay, at least three. Okay, and we're going to be comparing group 1 to group 2, group 1 to group 3, and group 2 to group 3. Okay, so we have already a bit more work computationally to do. Or at least the computer does. We necessarily don't. And we're going to be getting a little bit more sort of, I don't know, kind of more specific with the sort of conclusions we're making. Okay, because we're not just going to be saying that there is, you know, a big difference between all these things. We're going to be getting a little bit more granular with that. So what do I mean by getting more specific with things? Well, we have to be very careful with the language that we use, okay? So the null and alternative hypotheses that we're kind of used to seeing, at least from a sort of textbook world, remain about the same, at least structurally, okay? However, there is a major sort of thing we want to make sure that we get right, or at least specify each time we're doing a test like this, an ANOVA like this, okay? The null hypothesis, the kind of status quo, right, the norm, is that all of these groups, and I've got a little picture over here, is that all of these groups overlap so much with each other that there is no difference. There is no statistical difference between however many groups we're comparing. So all of the groups are equal. That's our null hypothesis, right? So if our p-value that we get from this test is over 0.05, then we say that there is not a big enough difference, or at least a statistical difference, between any of the groups, okay? Now this is where it gets a little different. Our alternative hypothesis is that at least one of these groups are different than the other one, or is different than the other groups, okay? So we are not saying that they are all different. We are just saying that at least one of them is different, okay? And then after that, we have to do a little bit more work to figure out what exactly is different, what group is different between the pairwise comparisons here, the group-wise comparisons, okay? So just to kind of make sure we're all here, the null hypothesis is that they're all the same. The alternative hypothesis, when our p-value is less than 0.05, the claim we go with is that at least one of these is different from the rest, okay? It could be one of them, it could be two of the groups are different than the rest, it could be three of the groups are different than the other one, are different between each other. There's all sorts of different combinations of things that could be. But right now, all the ANOVA tells us is that there is at least one of these groups is different from the rest. Okay. Whoa. Now, we are going to be working now with slightly different types of data sets. Okay, nothing too crazy, but we're going to have one column now that is made up of our response variable, or our outcome. Okay, usually that's numeric, or in our case, it's always numeric, and it's either continuous or discrete, but it's always numeric. And then we're going to have a column of names of grouping variables, essentially. But now we're going to have more than two. Okay, so that means that we're going to be shifting over into the language of saying what our predictor is and what our outcome is. Okay, so we're going to see how the outcome is affected by our predictor. And in the case of these one-way ANOVAs, our predictor variable is always the grouping variable, the thing that we are sort of using to separate the data. Okay, so I've got some examples here. When we can kind of, I'll answer the first two and you can kind of see where it goes from there. But in this case, which academic department in the sciences gives out the lowest average grades? Okay, and so you can kind of think of it, University of Wyoming, for instance, we have the Department of Statistics and Math and Biology and Physiology and English and Economics and blah, 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 blah. I just named 6 right there. What our predictor is the academic department, okay? It's the academic department. In that case, it's going to be the overall kind of umbrella term we use to say the things that our groups are a part of, okay? So in this case, it's department, okay? And our outcome variable, the thing we want to see, the thing that changes, or at least we think changes between departments, is our outcome. That's the average grade. We'll just say grades for now, okay? So our predictor is always the group. In this case, it's the kind of umbrella term for all the separate departments that there are in the university. And then our outcome is the numeric grade, okay? And this could be anything. This could be, 0 from 100 or 0 to 4.0, GPAs, whatever. Okay, the next question, next kind of scientific question here, a research question, is what kind of promotional campaign leads to the greatest store income at Christmas time? Okay, this is a little, maybe outside of your realm, if you're strictly a scientist, if you're in advertising or econ, maybe this might, be pretty apparent to you. But in this case, our predictor, the thing that separates our data, the thing that groups our data into different groups, is what kind of promotional campaign. Okay, so it's the type of campaign. Okay, in this case, maybe internet advertising, billboards, not Bill Burr, billboards, whatever, flyers, maybe. Those are just some examples. But those are different types of campaigns. Those are different groups. And then the outcome variable is, in this case, it's going to be income. Okay, and we can kind of see, I'll let you answer this one on your own, but you can kind of see the overall trend here. The predictor variable is always our grouping variable, department, type of campaign, some factor, okay, some thing, some character that we're using to denote different groups, and then our outcome is always numeric, okay, in nature, and meaningfully numeric too. Now, you probably have heard me say this plenty of times, and in fact, we worked with it sort of at the very beginning of our adventure. We work with groups, okay, and statistically, we call these groups factors. Okay, so the qualitative or categorical predictor, okay, categorical, different categories, is typically referred to as a factor, okay, in ANOVA, in the ANOVA world, okay. So our grouping variable, our categorical predictor, is usually called a factor, and that's what we saw in R when we had to make some of our groups a factor. We used this code here. Okay, this obviously wouldn't run in PowerPoint, but it would run in R, right? And we put the column of data, excuse me, in there that we want to turn into a factor. Okay. Now, each factor itself has different things in it. Okay, so different departments. The factor would be the department in general, and then within that column of data, within that factor, we have different levels. Okay, we have different levels, and the different levels are the specific names of our groups. Okay, so going back to the kind of department and grades question, the factor there would be department. And then within department, there are, 3 different levels, maybe statistics, econ, and I don't know, English or whatever. Okay, literature. The number of levels changes, right? The more groups you have, the more levels you have, right? That's kind of synonymous. But the factor, right, is the whole column that they're a part of. Okay, so you can kind of think of this as like an umbrella term, and levels as sort of the inner bits. Okay. Very cool. Very cool. And that's kind of it for new terminology. I only give this because there are different people that use different words for these. Again, not a big deal. We do try to stick with factor though, because that's what's used in R, as far as just turning characters into the actual factor here. Okay. Now, just like t-tests, we have some rules that we have to follow, or some things that we have to assume and check before we can do an ANOVA. Now, the first 2 are what we saw in t-tests. Okay, the first thing is that the population from which the samples are drawn should be normally distributed, whatever. Oftentimes, we don't know what the population looks like. So kind of going back to that idea of the central limit theorem, the means that we're grabbing, the means that we're sampling, also come from a normal distribution of means. Okay, again, that's some information that practically we don't so much need to worry about. Oftentimes, if our sample size is large enough, then we're good. Okay, this assumption is met, or this rule is checked when we have a large sample size. Okay, and what quantifies large is totally subjective, which is hilarious. And then our second assumption is independence. Okay, so that there is no one case that is dependent on another case. Everything is kind of randomly sampled and properly sampled. Okay, again, this is done when you're collecting data, not necessarily when when you have data that at least I give to you. Okay. So to be totally honest, these two are the ones that are kind of always assumed, not necessarily, you don't need to explicitly check these every time. You do want to make sure that you have a large enough sample size though. Okay. In this class for homeworks and labs and whatever else, you can kind of assume that these two are fine. Now here is the different thing. Homogeneity of variance. Okay, so variance among the groups should be approximately equal. Okay, well, what does that mean? Well, I don't want to sample. I don't want to be comparing groups that have, drastically different distributions. Okay, so for instance, if we were looking at GPAs again, or maybe grades, because that's a little bit of a larger scale. I don't want to be comparing statistics maybe that has an average GPA of like 3.0, maybe, I don't know, but with very little variance. So it's most people have a GPA of about 3.0 and only vary a little bit. It's not necessarily fair to compare that group to, I don't know, biochemistry that has a much larger range of GPAs. I'll say, I'm kind of speculating here. I'm making this up, but what the two distributions look like are totally different, right? So what I want to do is I want to make fair comparisons. Okay, I want to compare groups that have similar sort of variance, okay, between each other. I don't want to compare statistics that has a really narrow distribution of GPAs or of grades to biochemistry that may have the same mean GPA or mean grade, but varies much more. That's not a fair comparison to make. And I'll show you how we can check that here in the future as we go on. So with that, these first 6 slides here, a little bit of an intro, that's pretty much it. ANOVA is just t-tests on steroids. And we have to do a little bit more work. We have an additional kind of new assumption we got to meet. But otherwise, we'll see in R here how simple it is, which I think is great. R makes it very easy to do. So with that, I will see you in the next video.